When a company fails, it's so much more than just a headline. It means jobs are lost, investments are totally wiped out, and it can send these shockwaves all through the economy. So the ability to actually see that failure coming, well, that's one of the most critical challenges in all of finance. And it has a truly fascinating history.
It sounds like something straight out of science fiction, doesn't it? But for the last 50-plus years, some of the absolute smartest minds in finance have been trying to build basically statistical crystal balls to do just that.
And you've got to remember, for them, this is not some abstract academic exercise. This is the very core of modern risk management. Getting it right can save fortunes. Getting it wrong, well, that can trigger a crisis. So how did we go from just educated guesses to these incredibly powerful predictive algorithms? Let's find out.
So, let's dive in. Our story really kicks off back in the late 1960s with the very first systematic attempt to take a company's messy financial data and boil it down into one simple, clear signal of distress.
Here's the path we're going to take. We're going to journey through 4 truly revolutionary moments. We'll start with the first simple scorecard from Edward Altman. Then, we'll see the big leap to probabilities with Olson's work. Then, we'll jump into the 4th dimension, time, with Tyler Shumay. And finally, we'll land in the modern machine learning era with XGBoost.
This right here is where it all started. Back in 1968, Edward Altman's Z-score was an absolute game changer. And the idea, honestly, was brilliant in its simplicity. You just take a handful of key financial health numbers, things like working capital or retained earnings, and you combine them into a single score. Think of it like a credit score, but for an entire corporation.
You know what? It worked surprisingly well, but it had some major limitations. For one, it gives you a score, like, say, 2.5. But what does that actually mean? Is that a 10% chance of failure? 20%? The Z-score just couldn't tell you. Plus, it drew this really rigid, straight line between healthy and sick companies. And most importantly, it had this huge blind spot. It completely ignored the dimension of time.
Right, so the next big problem to solve was moving from a vague score to a real, concrete number. And in 1980, James Olson did that with logistic regression. It was a game changer. It basically takes all those messy financial numbers and squishes them onto this beautiful S-shaped curve. So the output is always a number between 0 and 1. And just like that, we had a direct probability of default. For the first time, you could actually say, this company has a 15% chance of failing in the next year.
But here's the thing. Even with that amazing leap forward to probabilities, a fundamental flaw was still there. Both the Z-score and these early logistic models were totally static. They looked at 1 year of financials and made a call. It was like trying to understand a whole movie by looking at just a single frozen frame.
And that, right there, brings us to the next huge revolution in this field. It was all about understanding that a company failing, well, that's not a single event. It's a process. It's a story that unfolds over time.
Okay, so just look at the difference here. The old way, that was all about the snapshot, the final grim picture right before the end. Then along comes Tyler Shumway in 2001, and he basically says, you're all looking at this wrong. The real information isn't in that last photo, it's in the entire movie leading up to it. Is a company that was stable for years and then suddenly collapses the same as one that's been slowly bleeding out for a decade? No way. The story is what matters.
So Shumway completely reframed the problem using what's called a hazard model. The question was no longer, will this company fail? Instead, it became, what's the risk it fails this year, given that it's managed to survive up until now? It's a subtle shift, but it forces you to think about time in a whole new way.
Okay, this table is the perfect way to see why this matters so much. If you're a static model, you only look at the year 2024. And what do you see? Firm A and Firm B look exactly the same. Both have negative working capital, both failed. But a hazard model gets to see Firm A's entire story. It sees the healthy 2022, the weakening in 2023, and then the final failure. It's learning the pattern of things getting worse, not just the final state. And that gives it way more predictive power.
And I mean, the results, they really do speak for themselves. Just by bringing time into the equation, Shumway's dynamic model blew the old static models out of the water. This wasn't a minor improvement, folks. This was a giant leap forward in our ability to see trouble coming.
So this focus on time series data was a massive breakthrough, but it created a new problem. All this rich, complex data needed even more powerful tools to really make sense of it all. And right on cue, something was brewing over in computer science,
machine learning.
And the idea that would completely take over was something called boosting. The intuition behind it is it's just fantastic. You start with a really simple model, one that's not very good. Then you look at all the places it made mistakes. Your next model doesn't try to solve the whole problem from scratch. Its only job is to fix the mistakes of the first one. And you just keep doing this, adding a new specialist to fix the last one's errors, until you have this whole team of models that, working together, are incredibly smart.
Now, for a while, boosting was this super powerful idea, but man, was it slow. That all changed in 2016 when Tianqi Chen and Carlos Gestrin released XGBoost. They took this brilliant idea and engineered it to run incredibly fast on huge datasets. And this was so important because, let's be honest, finance is messy. It's not linear. Rising debt might be totally fine up to a point, and then boom, it becomes catastrophic. XGBoost is a master at finding these complex, hidden tipping points that older models would just completely miss.
Okay, so what was the secret sauce here? It was a really clever mathematical twist. Instead of just chasing accuracy, XGBoost's main goal is a balancing act. As it's building its team of models, it's always asking two questions. Does this new model make us more accurate? And is it making our whole explanation way too complicated? By actually punishing complexity, it has this built-in discipline that makes it incredibly robust.
So XGBoost, it was a total game changer. We suddenly had this incredible new level of accuracy. But all that power came with a brand new and very, very serious problem.
We had created what everyone now calls the black box problem. The model could give you an amazingly accurate prediction, but it couldn't tell you why. And for a bank regulator, that's a complete non-starter. You can't just walk in and say, well, the algorithm told me so. You have to be able to explain your decisions.
And this tension, this is what led to the standard practice you see in banking today, the champion-challenger framework. The champion is that simple, trusted model, like logistic regression. It's the one you show the regulators. But behind the scenes, the bank is also running a challenger, a powerful black box like XGBoost, to see what the simpler model might be missing and to push performance higher.
But here's the exciting part. That gap between the two worlds, it's starting to close. New techniques, like one called SHP, are basically giving us flashlights to peek inside the black box. Think of it like a nutritional label for a single prediction. It can tell you exactly which factors, like falling revenue, push the risk score up, and which ones pulled it down. It's making the challenger more transparent than ever, which is kind of the holy grail here, getting the accuracy of the black box with the clarity of the simple model.
And so all of this leaves us with a really fascinating question for the future of finance. As our models get even more powerful and our tools for explaining them get better and better, we're going to face a choice. Do we stick with the simple answer that we can easily explain, or do we embrace the more accurate, more complex answer and trust our new tools to help us understand it? How we answer that question is going to define the next chapter in this incredible quest to predict the future.